Perfect. So hello, everyone, and welcome to the second session of Surfing the Ocean, the seminar of the ERC Ocean. Today, we have the pleasure to welcome two PhD students, one of Michael Jordan and the other one of Eric Moulin. We're going to talk a little bit about game theory and like a little bit of learning. So I'm pleased to welcome Nivasini, who is going to talk to us about repeated linear contracting for delegated learning. So the floor is yours and have fun.
Yeah, hi everyone. I'm Nivasini and I'm a PhD student here at Berkeley. Thanks for having me. I'm excited to present this work. So this is a joint work with Nika, Mike, and Stephen. So the broader context for context and motivation for this work is due to the fact is the emergence of various platforms and services that people can outsource machine learning to. So here in this slide listed are some examples of these services. So someone who's interested in using a machine learning solution to a task could outsource this task to these services, and they would do things such as collect relevant data and then train a model based on this and provide it to the person delegating. So this is like the broad motivation. And so the broad question we want to ask is, given this delegation problem, how do we design contracts, which are ways to evaluate and design payment rules? So how do we design contracts so that incentives are aligned for this delegation problem? So we're going to be building a model to model interactions between a principal and an agent in this setting. So the principal is the one who's delegating the learning task. So they have a task of interest and they're outsourcing this task to an agent who's actually performing the learning. And so in our model, there's two core challenges that we're aiming to model about interactions that happen in this way. So the first challenge that we're interested in is that there's no direct way for the principal to evaluate the agent's effort. So the principal either gets like a data set from the agent or a learned classifier. So there's not necessarily a direct way for the principal to evaluate this. And then the second challenge that we want to model is that before the start of this interaction, the agent doesn't necessarily know the principal's task of interest. So to address these challenges, what we'll allow is, for the first one, we'll allow the principal to be able to evaluate test accuracy of the learned classifier. So this is some noisy version of the true accuracy. And then the principal will design payments based on this test accuracy. And for the second challenge, we'll allow contracting to happen over multiple rounds. So that previous rounds, the evaluation in previous rounds and the payments in them will serve as feedback to the agent to learn more about the principal's task and refine its effort. Oh, by the way, feel free to interrupt me if you have any questions. Either message on Slack or just unmute yourself. Yeah.
Question, just does the platform that you presented before align to the fact that you do not see the principal task in advance?
Yeah, that's exactly right. We're not assuming that the principal's task isn't seen in advance, and it's just through payments that the agent receives, they'll learn more about the principal's task.
Okay, thanks.
So the protocol of this interaction kind of looks like this. So there's T rounds of interaction. So in each round, at the start of the round, the principal will announce a contract for that round. And then the agent looks at this contract and also has information about historical contracts. So like historically, the payments that it received. So given this, the agent will collect data and provides a learned classifier HT. The principal will then deploy HT and then measure performance of HT. And then the principal will assign payment based on the measured performance. And this payment is in accordance with the announced contract at the start of the round. So we'll instantiate what each of these steps look like, but this is the overall protocol of interaction. Yeah, so to further instantiate things, let's instantiate our model. So let's start with from the principal side. So we model the principal's task as some target distribution. So we're thinking of like a binary classification setting. So the target distribution is over a domain and a label set, a binary label set. And the principal's task is then to find a good classifier for this distribution. So find a classifier H that achieves a low loss on this distribution. Yeah, so I'm thinking of the 0-1 loss, but what's important is that the principal has some bounded loss functions. That's what we'll assume. And so this is a task. And then what we assume about the performance that's observed after deploying a classifier is that this observation is an unbiased estimate for the accuracy, the true accuracy of the learned classifier. So the true accuracy is this term one. Yeah, the true accuracy is this term. And then there's just some mean zero noise that's added to that. And this is what the principal observes. And then the principal's payment rule is a function of this measured, this measured accuracy. So in this work, we're going to focus on linear contracts. So linear contracts are just linear functions of the measured accuracy. So a linear contract is given by a coefficient. So at round t, CT is the coefficient of the linear contract. And that means that the payment of this round is CT times the measured accuracy of the deployed classifier. So it's just a linear function. So the reason we are focusing on this is because just in broader works, linear contracts are a focus of interest because they're simple and hence practical and used in practice. And in many settings, previous work has kind of shown that linear contracts tend to be approximately optimal and even more robust than even the actual optimal contract. So they enjoy a lot of nice properties. And so we're trying to see if our setting also has these nice properties with linear contracts. So moving on to the agent side. Like we said, we don't assume that the agent knows the D star, which is the task distribution. But instead, what we assume is that the agent knows that D star comes from some set of K possible distributions. They don't know which one exactly, but they know this entire set. And we assume that the agent can sample from any distribution in the set of K distributions. And we assume that the agent incurs a cost alpha for each sample drawn. So the agent has some sampling cost, which grows linearly with the number of samples drawn. And alpha indicates the constant, the cost of sampling one sample point. So a few notes here. We're kind of assuming just all distributions have the same cost of sampling, and that's alpha. And the other thing is we're not assuming any other cost for the agent. So in practice, the agent's going to have different costs for learning different classifiers. So like a more complex learning model would probably have a more cost, but we're kind of considering the setting where there's not too much difference in the cost of the classifier that the agent's going to return, or the bottleneck in the cost is really the cost of sampling. So so here we're mainly focusing on incentivizing sampling from the agent's part and not really focusing on other efforts of the agent. Okay, so those are the actions. And so the action again is the principal chooses a linear contract, the agent chooses a number of samples to collect and gives a classifier HT. So at this round, the principal's utility is the accuracy minus the payment. So since this is a linear contract, accuracy minus payment looks like 1 minus CT times measured accuracy. And then the agent's utility is payment minus cost. So that's CT times accuracy minus alpha times number of samples. So in this online setting, we introduce a notion of regret that we'll call aged regret. And H is a function class, a class of classifiers. And so we'll just think of some finite VC dimension class and let theta star be the least loss, or the 1 minus theta star is the best accuracy that any classifier in this class achieves on the distribution D star. And so what H regret it does is, like any other regret notion, it considers some baseline utility and compares how the online cumulative utility compares to this baseline utility. And the baseline utility is what is achieved when you always deploy the best classifier in the class H without doing any sampling or offering any payments. So for the principal, the baseline utility is T times 1 minus theta star. So that's the optimal accuracy times just the number of rounds. And for the agent, it's 1 minus theta star times the sum of linear contracts over all of the rounds. Yeah. And so we can write out what H regret is as just the sum of utilities minus the utility in of the baseline utility. So writing that out for the principal and agent kind of looks like this. So we're going to be considering what the principal can achieve when they're contracting with an agent that's rational. And the model of rationality that we're going to assume in this work is that the agent achieves sublinear H regret, and sublinear in this quantity ST, which is the sum of all linear contracts that are offered over all rounds. And so the result that we want to show is that if the agent has sublinear in ST H regret, then the principal can achieve H regret that's sublinear in the number of rounds. So we'll show this result, and then we'll also show that the agent can achieve this this kind of rationality by providing an algorithm that will achieve this regret rate for the agent. So we'll start with how the principal can achieve sublinear in T regret. So and in order to do this, so we'll give a contract that the principal can use, and then this contract will depend on the regret rate of the agent. Both the contract and the resulting principal's regret rate will depend on the regret rate for the agent. So again, the regret rate for the agent is this ST to the power X. And so since it's sublinear, this is for some X less than 1. Yeah, so what the principal will do is essentially for some number of rounds N less than T, they'll offer all of their utility to the agent. So that's contracting with coefficient 1. And then they'll deploy the agent provided contract. So that's for the first N rounds. And then for the later rounds after N, the principal completely shuts down contracting. So there's no payments that are provided. And the principal instead just picks one of the previously provided classifiers, H1 to Hn at random, and deploys this for the remaining rounds. And by choosing N to be of this rate, T to the 1 over 2 minus X, we can show that the principal achieves T to the 1 over 2 minus X H regret. Again, this is using the assumption that the agent would achieve N to the X because the sum of contracts here is N. So the agent is, we're assuming the agent assumes N to the X regret. And so if that's the case, then the principal would choose a contract of this form and achieve this rate. Yeah, so to analyze the previous contract, so we can, to bound this H regrets, so we can first consider the first N rounds and just assume that maximal regret occurs in each of these rounds. So we can just upper bound that by N because the regret in each round is upper bounded by 1. And then in the last T minus N rounds, the regret, so we can upper bound the regret by measuring the quality. So the regret is only due to suboptimality of the classifier that's deployed because no more payments are being made. So what we want to do is look at the quality of the classifier that's deployed. So this is in expectation, the loss of the random H that we pick minus the best, minus theta star. This quantity is just related to the regret. So it's 1 over N sum of the excess error of classifiers deployed in the first N stages. So the summation here is upper bounded by the agent's regret. And so it's agent's regret divided by n. So that's n to the x over n. So we get 1 over n to the 1 minus x. And yeah, so we're applying 1 over n to the 1 minus x over t rounds. So it's t times this rate here. And so that will give us an upper bound on on the principal's regret. Yeah, so what we'll like we said before, we're gonna say we're gonna give an algorithm for the agent to achieve sublinear h regret, sublinear in st. And the way that we'll show is that it's st to the power 2/3. And what that'll mean is that the principal can then achieve t to the 3/4 h regret. So we'll describe we'll describe the agent's algorithm in this contracting protocol. So there's 2 phases to this. So there's 2 components to describing the agent's algorithm. The first is the sample is how the agent collects samples, and the second is how the agent selects classifiers. So we'll focus on sample collection first. So the consideration for sample collection, the first consideration is that we want the agent to limit the number of samples they collect. So again, since the agent has cost linear with number of samples, and since st to the 2/3 is the rate that we want to achieve, we want to limit number of samples to be of the order st to the power 2/3. And so to do this in an online way where we don't know st before, like we don't know the sum of all contracts beforehand, like at any earlier round, what we'll do this in an online way is that each round will ensure that the number of samples that we collect is st prime. So at round t prime, it's st prime to the power 2/3, which is just the sum of contracts up to the current round that we're in. And so st prime is just sum of contracts up to round t prime. And so sort of just inductively, like by the time we reach the maximum number of rounds, we'll just ensure that all samples we collect is limited to st power 2/3. So that describes the number of samples that we're collecting in each round. But for the next thing that we have to consider is which of the distributions we sample from. So there's k different distributions, and we just propose uniform sampling. So just pick a distribution at random and sample from that distribution. So for the classifier selection, we'll need to do a combination of exploration and exploitation. And what we'll propose is doing exploration during sample collection rounds, and then exploitation of non-sample collection rounds. And recall that we're limiting the number of sample collection rounds. And so this limit will give us the right exploration-exploitation trade-off. So focusing on the exploration, the purpose of the exploration is to determine which of the k distributions is relevant for the task. And so here's like a natural approach for doing this. So what we could do is, so at every round, keep track of all the samples we collect for each distribution and learn a classifier based on that sample set. So we get resultant classifiers, G1T to GKT. So where GIT is a classifier that's trained on samples from distribution DI up to round T. And so then we'll evaluate these classifiers, and then we'll say that the distribution I that results in classifiers with high accuracy is a relevant distribution. And so to determine the resultant accuracy of distribution I, that's just summing payments from deploying a classifier based on I, and like at rounds that the classifier based on I is deployed. And if this sum is large, then we can say that distribution DI is relevant. So that's like one approach. But the problem with this approach is that GIT could change with time. It could be like, it could be very sensitive and just keep changing with time. And so what could happen is classifiers that are trained on some different distribution than D star could have high variance in terms of the loss on D star. And so we can't get reliable estimates on the performance of classifiers from other distributions on the target distribution. If the distributions based on if the classifiers based on distributions keep changing rapidly over time. So to fix this, instead we'll do exploration in a phased way. And so what we'll do is so rather than keep changing classifiers based on distributions, we'll keep them fixed for some number of rounds and then explore these classifiers. And then after finishing this exploration, we'll update the classifiers. So this exploration is now going to happen in phases rather than it's going to happen in phases. So the way we'll come up with phases is, again, we're doing all of this only during rounds that we're collecting samples. So we'll divide those rounds into different phases, and the first phase has length 1, the second phase has length 2, and the length of phases just keep doubling. So the length of phase J is 2 to the J minus 1. So we just have this like exponential growth in the length of phases. So the number of phases is log st to the 2/3, because st to the 2/3 is the number of possible rounds in of sample collection. So log of that number is just the number of possible phases. And so we see that in phase J, we have at least 2 to the J minus 1 samples that are collected in that phase. And so like we previously said, we're at the start of a phase, we're going to fix the classifiers that we're going to explore. So at the start of the phase, we look at all the samples that are drawn from a distribution up to the start of that phase. So Qij is the samples collected from Di in previous phases 1 to J minus 1. And then we find a classifier Hij through like empirical risk minimization relative to H using the sample Qij. And we're not going to change these Hijs throughout the phase. But throughout the phase, we're just going to pick one of these K classifiers uniformly at random. At the end of the phase, we would have identified H star J as the best classifier of phase J, which is one of these K classifiers. Yeah, so to analyze what exploration is doing, so exploration is just uniformly exploring K options a certain number of times. So we're getting uniform estimates and precisions of the losses of the K candidate classifiers. So for each Hij, we're estimating the true loss on D star to precision square root K over 2 to the J minus 1, because each Hij is queried 2 to the J minus 1 over K times, which is the length of the phase divided by K, since we're just uniformly querying. And then, so because of this, we can say that at the end of the phase, the classifier that we pick, H star J, is order 1 over square root 2 to the J optimal among the K classifiers. So this property is just because of the length of phase J. Next, we'll show that it's not just optimal among the K classifiers of this phase, it's also close to optimal compared to theta star itself. And this is because the classifiers at the start of the phase themselves have good enough accuracy because they're built on sample sets that are large enough. So since D star is one of the K classifiers, let's say like Di star is D star. So that means one of the ERM classifiers at the start of the phase is an ERM classifier based on samples from D star. And it's based on like order of 2 to the J over K samples from D star. And so this inequality here is just like a standard BC dimension based error rate, where D is like the dimension of the function class. And so, yeah, so the bottom line is like the classifier we pick at H star J is order 1 over square root 2 to the J optimal compared to theta star, which is the best classifier for D star from the class H. And so the next kind of classifier selection we do is when no samples are collected. And so in this case, we're going to switch instead from exploration to exploitation. And the idea is we just want at this point to figure out a classifier that we know has good enough performance based on the exploration and deploy this. So what we'll propose is, suppose the last collected sample was in phase J, then select H star J minus 1. So the best classifier of phase J minus 1. And the reason is because we've completed phase J minus 1 and performed enough exploration that we can be confident that H star J minus 1 has good accuracy. Yeah, so let's say the index of round with no sampling is T and S. So we can relate J to T and S, because the index of previous sampling phase is of the order log of T and S. So, and so what that means is the classifier deployed at T and S is less than or equal to theta star plus 1 over square root T, where T and S is the current index of time. And so to analyze the regret in non-sampling rounds, let's first so let's take the best classifier from a certain phase, and let's upper bound the regret that we get from applying this classifier. So so we can upper bound this by getting an upper bound on the max index of non-sampling rounds where this particular classifier is selected. And so, so this would be a max index if the next index is a sampling round of the next phase, so phase J plus 1 instead of J. And what that means is any future non-sampling rounds will then choose H star J instead of H star J minus 1. Yeah, so the number of samples that are drawn up to, so since we're doing this phase transition, that means the number of samples that are drawn up to this phase is greater than or equal to 2 to the J plus 1. So if we take the sum of all contracts that are up to a T of NSJ, that's upper bounded by 2 to the J plus 1. And so now, again, we can multiply the suboptimality of H star J minus 1 with the contracts that are offered at this level of suboptimality to get an upper bound on regret due to this classifier. And so that's just summing up to TNSJ, CI times suboptimality of H star J minus 1. And so the previous slide, we saw an upper bound on sum of CI, and then we know that the suboptimality of H star G minus 1 we've also seen an upper bound on the suboptimality of H star J minus 1. So putting that together, we get that due to H star J, we get a regret of square root 2 to the J. And finally, we're just going to sum over regret due to H star J minus 1, where we're summing over J for all phases. And so again, the number of phases that we had was log of ST to the 2/3. So summing over this, we get an upper bound of regret of ST to the 2/3. Yeah, so putting all of this together, what we've seen is in the sampling round just lasts for ST to the 2/3 number of, it's just at most ST to the 2/3. So that's a direct upper bound on regret in those sampling rounds. And then in non-sampling rounds, we've just seen that, again, we have an ST to the 2/3 regret upper bound. Yeah, so this just shows that the agent is able to achieve ST to the 2/3 regret upper bound. So bringing this back to what this means for the principal is that, so we described this contract where the principal could use where they could contract for a certain number of rounds and then offer 0 contract in later rounds. So using that, the principal would get an H regret of T to the 3/4. And so then we could ask if the principal can do better than T to the 3/4. And the answer is that with an agent that has as good as or even better regret rates than the one we just described, the principal cannot do better than T to the 3/4. So that's saying that so if you're contracting with an optimal agent, so an agent that has optimal regret rates, then the principal necessarily achieves T to the 3/4 H regret. So for this lower bound on the principal's regret, first we'll consider lower bound of regret due to payments. And and to do this, let's consider what payments imply for agents regret. So the agent's regret is at least 1 minus theta star ST. So this is baseline payments minus total payments. And so when agent has H regret sublinear in ST, we know that the total payments is linear in ST, is like omega ST. And so this implies that principal's H regret is ST. So H regret due to payments is omega ST. Due to suboptimality of the classifiers deployed. So what is an agent that has ST to the 2/3 regret will collect at most ST to the 2/3 sample. So an upper bound on agent's regret will give you an upper bound on the number of samples that the agent collects. And the idea is that an upper bound on the numbers of sample necessarily implies a lower bound on the suboptimality of the classifiers that are deployed. And so that's what's giving this proposition. So we'll talk about the idea of the proposition later, but applying this proposition, we get a lower bound for the principal's regret, that's ST plus T over ST to the 1/3. And then the optimal choice of ST is to choose ST to the 3/4, and that gives us the lower bound on principal's regret rate. Yeah, so let's talk about the intuition for the proposition. So the proposition is saying that an upper bound on number of samples is a lower bound on suboptimality of classifiers. And so this is reminiscent of like standard lower bounds in like VC dimension-based lower bounds. But the only difference, so VC dimension-based lower bounds with just M samples from a distribution will have, like in the worst case, excess error of omega 1 over squared M. But what's different in our case is that we have more than just samples from the distribution D star. What we also have is access to queries where we can give a classifier and we get estimates of the accuracy of that classifier on D star. So we have query access to LD star H. So even if the agent has just samples M times, there's T possible queries of this form. And so we need this lower bound on suboptimality, even in the presence of this query axis. And that's what this proposition shows. And the intuition of this is just that the queries aren't very useful in a worst case, because without any additional samples, it isn't clear which classifiers to pick in query. And so the standard learning lower bounds would hold. Yeah, so I'm going to be concluding with just comparison to the non-delegation benchmark. So what we've shown right now is what the principal can achieve through delegation with a rational agent. But what happens if there is no delegation? Then what can the principal achieve? So this is essentially analyzing the agent's H regret with CT equals 1. So where the agent just gets all of the utility. And so we've already shown that this is order T to the 2/3, upper bounded by T to the 2/3. So that's what's achievable without delegation. And what we've then shown is that delegating to an agent with optimal H regret rates is at least T to the 3/4. And we've also shown that it's upper bounded also by T to the 3/4. So T to the 3/4 is achievable. So even though the principal gets sublinear regret rates through linear contracting, it's still a strictly worse rate than what the principal can achieve without delegation and doing the task themselves. And this kind of intuitively makes sense because the cost of sampling grows linearly, but in terms of accuracy, you get diminishing returns in terms of utilities. And that kind of is why you get this gap in rates between with delegation and without delegation. Yeah, so that's all I had to say. Yeah, happy to take any questions.
Thank you, Nivasini.
Yeah.
So are there any questions? I have a couple actually, and I want to understand more about the fact that you fixed alpha as the payment. or for the agent point of view, and I don't understand. Can you I know that you already said it, but can you repeat why you just fix that alpha?
So alpha is the cost that the agent faces from collecting samples.
Okay.
And it's, yeah, so we're not imagining that the cost of collecting samples changes with time. It's just a function of the number of samples that you collect.
Okay. Okay. And another naive question would be like, what happens? How do you have any developments on this kind of model? Like, what happens, for example, when you have like one principal and many agents, and maybe these agents are in competition? Do you?
Yeah, we haven't explored that at all. Yeah, so perhaps this gap between what is achievable through delegation, what is achievable without delegation. So there's this gap between like 2/3 and 3/4, right? So with competition, it's possible that that gap might not exist. But yeah, that's not something we've thought about.
You are saying that might not exist?
Possibly, but we just haven't thought about it.
Okay. And if I may, just one last question, maybe, and I don't know, is it the choice of like splitting like exactly in the same amounts, like the exploration phase and exploitation phase, optimal somehow? Can you achieve like having different kind of other exploratory phase and exploitation phase?
Yeah, so it is optimal because yeah, so kind of yeah, so that's another result that we can show, and it's the same argument as why the principal cannot achieve a higher regret than t to the 3/4. But it is optimal, sort of, and the reasoning is sort of the bottleneck actually is the number of samples collected, which is the exploration phase. And so you kind of need that 2 to the like 2 to the 3 t to the 2 to the 3 exploration phase. And so you need that for the suboptimality of classifiers. So 2 to the 3rd will give you like 1 over t to the 1/3 suboptimality. And t times the suboptimality is again t to the 2/3. So what this trade-off is doing is balancing cost of exploration and regret due to suboptimality. And so you can't. So this is exactly balancing both costs. So you can't do better than that.
Okay. Are there any questions? Well, if not, let's thank Nivasini again. Thank you.
Yeah, thanks everyone.